So far, you have differentiated using the product rule, the quotient rule, you've learned about substitution, and you have already learned at the start about first principles. Today, we're going to find out about the derivative of exponential functions using first principles. So let's start with f of x equals 2 to the x. F of x equals 2 to the x is an exponential function, and if we substitute in x plus h, it's a little bit different because where x is, we put x plus h. So using first principles that you have done before, we substitute in. The next thing is laws of indices. You have to remember that if you have to the power of and there's a plus sign, it actually means it was multiplying them. So this means 2 to the x times 2 to the h. We could pull out a common factor of 2 to the x, and in fact you could also bring it to the front like you did with sine and cos derivatives when you were using first principles, because you're substituting in as h tends towards 0, the 2 to the x can just come to the front. If we put in 0.001, you can explore using your calculator what happens there, and what you'll find is 2x, I get 0.693. What you'll find is whatever you put in, 0.00001 if you want, then you'll find that it's 2 to the x, but times a very small value that's less than 1, okay? Do the same for 3 to the x. If you go to 3 to the x and substitute in the same way, remember that addition means you've multiplied with the indices. When you click them, it means you add. So let's split that up. Let's bring out the common factor of 3 to the x and bring it to the front, just the same. And now let's explore as h tends to 0.001. Again, if we use the calculator here, you'll get 3 to the x, and you'll get a value that's just a bit bigger than 1. So that means that you will find that your 3 to the h minus 1 over h is a little bit bigger than 1. What does that mean? For a very small h, you'll find that 2 to the h minus 1 over h is a bit less than 1, and 3 to the h minus 1 over h is more than 1. Something happens in between these two. So when there is a function that lies between the two of them, it's known as the natural exponential, and in fact, you'll find that if you use your calculator to find some points, the e to the x will look like that between the 3 to the x and the 2 to the x. If you use your button in the calculator, you'll find an actual value for e to the 1, and you'll find it's between the 2 and the 3, and in fact it's 2.71828, on and on and on. It goes to infinity, and it's the natural growth curve, the natural exponential. So what's the derivative of this? If we have first principles again, then you'll have e to the x plus h minus e to the x. Again, use your index rules, pull out a common factor, and then what we're going to do is get that e to the x to the front again. Let's substitute in 0.001 or whatever small value you want to try, and what you'll find this time is this part here actually tends to 1, and there's your derivative. So the derivative of e to the x is just e to the x. How nice is that? The derivative of e to the 3x, we do the same way, except remember you're putting x plus h where the x is, and then you can separate them again, pull out the common factor, bring e to the x to the front, and this time when you put in 0.001, you get 0.003 there, and surprisingly, when you put that in the calculator, it tends to 3, and what you get out is 3e to the 3x. That means that when you differentiate exponentials, it's really easy. You get e to the 3x, you get e to the 3x, and the only thing you worry about is the chain rule coming out. So let's try some. You might see exp or e to the x. I'm a fan of e to the x, so if you see it like this, you'll see I'll instantly write it as e to the 4x. What happens there? The derivative is e to the 4x, but the chain rule brings out 4, and that's it. Let's go far more complicated, 2x e to the x squared, then u is 2x and v is e to the x squared. So what can we do there? I'll try to move it this way just now. If you have 2x, that will go to the 2, and if you have e to the x squared, then what you'll have is e to the x squared still there. It's always the same, but the 2x comes down as the chain rule. That is u dash v plus uv dash, so 2e to the x squared times 2x e to the x squared. And then you can pull out a common factor. They both got a multiple of 2. They both have e to the x squared, and that's your answer. Okay. So you can do it with the chain rule. You might have the product rule, you might have the quotient rule. But actually it's just e to whatever it was in the first place, and then the chain rule come down. If you find it super tough to remember, you can use substitution as well. Right, what are you going to do? You're going to do exercise 11 from the Scholar book, and I've not put the page number there because I thought, you know what, you could just use this instead. But if you do want to, then go to page 8 in your PDF and you'll find the Scholar information there. And then afterwards, you can go to the slides after this for all your solutions. If you want, then I've just went through that really fast. You can find in page 248 your answers to the exercise. So only look at this for handwritten solutions to see how I've got to it. But if you just want to check your answers straightforward, then 248. That's exercise 11. Okay.